So in last class, we studied that maximum node-weighted independent set in a chain graph, basically. Okay. So I think if we go back, so this is the chain graph. Okay. And each node is associated with some weight. And for what is the maximum independent set, uh, that we can find out. And remember, we are not only interested in the value of the maximum weight, but also in the set or the set of vertices which which can be which can be which can result the maximum weight. So what I this is a home assignment actually. Okay, this is a home assignment. I will say that home assignment. Okay. Write a C or C++ or Java program to implement the max weighted independent set problem. Okay, and you need to share me the program so that I can just run it in Linux. Okay, I can just run. Suppose you give me the code and the file name is max wis maximum weighted independent set dot c or dot java minus o a dot out. I should do, and I should get it. I mean, if it does not work, I will not go into it. Okay. So anything, I want something like this. Okay. And you can think of a deadline of say next next say Saturday. Okay. Now today we will deal with a similar problem, which is the weighted interval scheduling. Weighted interval scheduling. So if you remember during the learning of the greedy algorithms, we discussed a number of interval scheduling problems. One was to accept the maximum number of intervals, okay, given a single resource or single computer to schedule as many intervals as possible, uh, so that they do not conflict with each other. The second problem was, okay, the same set of interval will be given with SIFI, but now you have freedom of resources. You minimize the number of resources that is required so that all the intervals can be accepted. And there is the third version where each interval is of the form TI-DI. TI is the duration, DI is the deadline, and we want to schedule all of them on a single machine. But then somebody is bound to miss the deadline and some lateness is created, and we want to minimize the max lateness. Okay, something like that. So all of these are greedy in nature, and we solve these problems. Now, one thing we did not notice in that problem is that each interval is just an interval. I mean, it doesn't have any associated value or weight. But in practice, if you think of practice, then sometimes intervals can have some value associated with it. Uh, Let me motivate with an example. So let us say these three intervals are there. This person is giving, say, 7. This person is giving 6, and this person is giving you 10. Right. So if you if you take this if you take this 10, then probably you are not benefiting. You are actually maximizing the number of intervals by taking 7 and 6. So you're actually maximizing the number, and as well as you are maximizing the total money earned. Okay. But suppose now I modify this number. I modify this number 10 to something like, let's say, 14. Then what happens? Then if you take the 7 and 6, that increases your count. Okay, you select the maximum number of intervals that are accepted, but you do not maximize the money. Okay, but rather if you did not take these two, if you took this one, then probably you maximized your money. Okay, and that is very natural in a practical scenario. So people will give slots to those persons who give higher money. Okay, so the problem, I hope this is enough motivation for the problem. So the problem is about each interval is associated with some weight. Okay, instead of just the number, each interval has an associated weight. Okay, let's say Wi, which is non-negative. And we have to accept that subset of intervals such that the total weight is maximized, something like that. So let's say, so goal, what is the goal? So let's say S be the set of intervals given. So goal is to find a subset, let's say IS, okay, such that you take the weight of every element in the IS, okay, and this thing is maximized. Okay, so this is the interval. This is something known as weighted interval scheduling. And also remember in this case that, I mean, because this is a case of single resource, the problem of conflict still remains. It's not that the problem of conflict goes away. So I will write that conflictings or overlapping intervals cannot be taken. Because if you take conflicting intervals, then even though they give you maximum rupees, but they cannot work together. Okay, if one works, the other has to skip because there is only one machine. Okay, so you cannot take conflicting intervals. So the conflicting or overlapping intervals cannot be taken. Okay, that criteria is still there. So this is the problem. So now what we try to do is if we think of any kind of greedy algorithm, then initially we may think, okay, I want to maximize the number of non-conflicting. I want to accept those which are not conflicting, as well as I want to maximize their weight. So why not let us sort the intervals based on their weights, okay, from high value to low value, and then I only take as many high values as possible, such that they do not conflict with each other. Okay, so but the example I gave, that suppose you have uh, suppose you suppose the intervals are like this. Okay, let's say this is your 10, this is your 6, this is your 5. So what happens if you sort these numbers? These are the weights basically. If you sort this number, 10 will come 5 and you have to take 10. So once you take this, to remove conflict, you cannot take this 6 and 5. You cannot take. So you are gone basically. So rather, if you take 6 and 5, then your total, then you cannot take 10. But in that case, you actually maximize the weight, as well you remove the conflict. Okay. So it may not be obvious if I just uh, sort the intervals by their weights. So you can think of some sort of greedy technique, but it can be shown that no natural greedy algorithm is actually appropriate. There will be some kind of counterexample to find the flaw. So we try to solve it using the technique of dynamic programming. And remember, from the idea of how we solve the dynamic programming problem in the uh, chain case, in the maximum weighted independent set in the chain. Okay, how did we solve that problem? So we actually considered the special equation where there are overlapping subproblems. We must be very aware of that concept, that there should be some overlapping subproblems. So how do we formulate such equation for weighted interval scheduling problem? So so let's say that so what we do is we try to uh, understand certain ideas before proceeding to the problem, uh, because this is a little more general. Okay, so let us say that we have n requests. Okay, n request means n intervals. So let us say we have n intervals of the form, let's say 1 to up to n, and each request is coming in the form uh, request I, or interval I is of the form SIFI. The same idea, basically, basic things. I'm just recapitulating maybe. And each interval has a value or weight. So for request I has a value, associated value, I or weight. Okay. So whatever it is, I designate it as, let's say, WI. I designate it as WI. So, so as I said, the goal is to find out a subset such that sum of the weights is maximum. Okay. So what I do, so I sort the intervals based on their increasing finish time. Okay. So just like earlier, So I sort intervals based on finish time. That is fi value. So let's say that sorted order is, let's say, f1 is less or equal to f2, f3, fn. So remember, these are not exactly the same as these fs. I mean, I let's say maybe I am confusing. So let's not say this. Let's say there is some sorted order. I mean, it may appear like these intervals are sorted exactly like that. So we sort them in such a way, and let's the sorted order be some ordering. Let's say f prime one. So what is this f prime one? F prime one is some f prime one is, let's say, suppose f5. That is the smallest in the finish time. So if this is a situation, if we and we can say that these intervals comes before this, something like that. So now in this ordering, in this sorted ordering, okay, I designate one term, something like pj, okay, pj be the largest index I, which is smaller than j, such that I and j are disjoint or non-overlapping, let's say. So what does this mean? What does this mean? This means uh, so if you look at the intervals in left to right order, okay, if you look at the intervals in left to right order in this sorted finish times, okay, it may happen that suppose I have, let's say this is the line actually, ij line. This is some number line. Let's say this is my jth interval. Okay. Now, what is my j minus 1th interval? Let's say this is my jth interval. What is my j minus 1th interval? Let's say this. What is my j minus 2th interval? Let's say this one. What is my j minus 3th interval? Let's say this one. So this is j. I'm just saying this is my j minus 1. This is j minus 2, j minus 3. Let's say this one. Now, if I look keenly on the set of intervals, this set of intervals, then I see that j actually conflicts with this j minus 1, j minus 2, and but it does not conflict with j minus 3. It does not conflict with j minus 3. Hello? Yes, yes. So if you look at j actually conflicts with j minus 1, j conflicts with j minus 2, but it does not conflict with j minus 3. It does not conflict with j minus 3. So that means my pj my pj will be assigned to j minus 3. And this is the definition of pj. Pj be the largest index I. So this also has to be the largest index. Okay, there may be some j minus, suppose 5 earlier interval, j minus 5. That may also not conflict with j. But I will not take pj equal to j minus 5. I will take j minus 3 because this is the largest index, some index I. This is actually I, j minus 3, largest index I, such that, and that is smaller than j, and it does not conflict with j. Okay. So that essentially means, in a sentence, that essentially means anything, any interval between pj and j. Remember, excluding pj, excluding pj. So any interval between pjth interval and j, excluding pj, conflicts with j. Right? pj is the largest one, that is disjoint. So pj does not conflict with j, definitely. But anything higher than pj conflicts with j. Of course, j itself conflicts with itself. I cannot take that. I mean, I should not consider that. Anything between, anything higher than pj conflicts with j, except of course j. So the motive is that I cannot take those intervals, basically. Okay. So now with that idea, I will move forward. Okay. So now what? So if you think about, then what is the pj value for all j actually? So what is pj for all j? What is the pj value? Okay. So it may so happen. So this is clear. I mean, from this definition, if I can find out some largest index I, which is less than, strictly less than j, such that I and j are disjoint or non-overlapping, then that is my pj. But it may so happen that at this point of time, I have a j, but I do not find any pj. Okay. So in that case, I will say pj equal to 0. If I find no such I. So if that means what? That means all the overlapping, all the intervals that are smaller than j, I mean lesser the interval identities that are less than j, they're all actually overlapping with j, and I cannot find any index pj which is actually non-overlap. So that time I assign pj equal to 0. That means no such identity is there. And remember, this is some number. J mean the interval numbers are actually 1 to n. Let's see, the n intervals 1 to n. So that means 0 means there is no such interval. Basically. That index is 0, that means no such interval. Okay. So now what I do, I try to make some argument. I try to make some generic argument. What is that? See, what is my goal? If you remember, the goal is to maximize the weight of some set. Let's say S. I is an element of S. This thing I want to maximize where S is a subset of this 1, 2, ... n. So 1 to n, these are n intervals. S is some subset such that I take that subset and I sum up their weights, and that is maximum, is max subject to the condition that non-overlapping S. That means whatever S you take, you cannot take arbitrary S. I mean, S should be a collection of such intervals, they are not overlapping. Because if they are not overlapping, then only you will be successfully able to schedule them, otherwise not. Okay. So these are the two things. Now, and their weight. So this is the weight. So let's say this is, let us designate that as opt. Opt when I have this n. So I designate this as opt n. Okay. So I designate this as opt n. Okay. So what is my opt n? I now try to argue what is my opt n. Okay. So I try to give an argument. Again, I make this question, important question, that does nth interval is included in opt-in? Is nth interval included in opt-in? This is my question. Again, there are two cases. One is nth interval may be included in the opt-in, and the second case is nth interval is not included in the opt-in. And in that case, I try to form sub-problems. So case one, I say not in nth interval in the opt. I use this symbol actually. Let's say not nth interval in opt-in. Let's say this is the case. So in that case, if you think that nth interval is in the opt-in, then what is the final solution? If you remember that any interval between Pn and n, I cannot take. Okay, I cannot take any interval between Pn and n. Why? Because I have taken n. So all in intervals up to Pn. I mean, Pn is the first. If I come from nth interval, I start my journey from the nth interval and I start moving to the left, n minus 1, etc., etc. The some index Pn will be there. Okay, and there I find first non-overlapping interval. So possibly I can take that, possibly. Any other ones between Pn and n I cannot take. Okay, so that means up to, so I have to find an optimal solution. I mean, I need to find an optimal solution, optimal solution in the range 1 to up to Pn. This is my next subproblem. And then what I'll do, I will add the weight of n, this nth interval. So what will be the case one solution? It will be some optimal solution when the index is, last index is Pn plus the weight associated with it. This is the optimal solution. Okay, this is the optimal solution. In case one, when nth interval is in opt. Case two is nth interval not in opt. So nth interval does not contribute in opt-in. Remember, opt-in is actually the weight. I'm not Still now I'm just arguing, but opt actually is the weight function solution. I'm thinking of optimal weight. So later I will, using that recurrence, I will get the solution actually, the set. So nth interval not in opt. So if nth interval is not in opt, so in this sequence 1 to n, nth interval is not considered in the opt. So the optimal solution up to n, first n minus 1 interval, that should be my optimal solution. So in that case, opt should be, it should be opt. The solution is, I need to find out opt n minus 1. Okay? I just need to find out opt n minus 1. Okay. So what should be my recurrence? I should actually take the maximum of these two. Okay. So that essentially means opt n should be max of these two things. One is wn plus opt n, comma, opt n minus 1. So this is my recurrence. Opt n is actually max of these two. Okay. And this actually we can generalize actually. We can make this a general basically. Instead of n, I can give any particular index value basically to make it general. Opt j is essentially max of wj plus opt of pj, comma, opt j minus 1. This is something general and true for all j basically. Okay. So this is my recurrence relation. Okay, and if you see this recurrence, you will see that there is considerable overlap between opt pj and opt j minus 1, or similarly opt pn and opt n minus 1. So opt n minus 1 is actually all the set up to n minus 1 to n minus 1 intervals, and pn, in case pn is 0, that means if everybody is conflicting, then basically I don't have anything to say. Then opt pn is 0, that means no interval can be taken. So opt pn 0, so only the wn is the contribution. If you take the last interval, you cannot take anybody else. That means only weight of w. Or if you do not take the last interval, then what is the optimal solution for the first n minus 1? Okay, whichever gives you better solution, that you should take. So this is the recurrence equation. So once you have the recurrence equation, again, as I said, that you can call a recursive routine to calculate this thing. This is a recursive routine, but this cannot be done because recursion will lead to, maybe it will lead to exponential number of calls to opt to compute this opt. So rather, again, we go into the memoization scheme, like we fill up a table basically. Okay, we remove the redundancy by memoization, and we fill up a table. Okay, what is this table? This table is like this. I have an array of size n, and this is my opt 1. This is my opt 1. This is my opt 2. Opt 2 means optimal solution, optimal weight up to 2 intervals. Okay, and so on. Opt 3, opt 4, and this is my opt n basically. Now, remember, one thing is very important here. So if you basically you start fill up with opt 1 and 2, if you fill up opt 1, then opt 1 means actually you have to take that one to maximize your benefit. Opt when two up to first two intervals, if they are non-conflicting, then you take both. If they are conflicting, you take the one which has the maximum weight. So after filling up these two, the third one, actually you can use this recurrence relation to fill value. What will be the value? It will be maximum of opt weight 3 plus opt of pj, p3, opt of p3. What is p3? Or opt of 2, basically. Max of these two. What is opt of 2? That means if you take this, then opt p3. P3 means what other intervals are not conflicting. What is the of p3? What is the largest index? What is the largest index? What is the largest index that I cannot take? Okay. So let's say I cannot take 2, but I can take 1, let's say. So I can take 1. So what will happen? This W3 will be taken, and opt 1, I already know. I already know what is the optimal solution up to this point. Okay. So that, and then opt 2, in case this 3 is not in the solution, you do not take 3, then what is the thing? Up to opt 2 you give, and opt 2 is already computed. So you take the max of these two and you store it in the opt 3. In this way, so what is my saying is that to compute any opt j in this table, in this array, you need actually only opt pj and opt j minus 1. So assuming that all your, so say this is j, I can compute j only if opt j minus 1 is filled up and pj is also filled up. Then pj, hopefully this j I'm computing, all the previous entries have been filled up. So if pj belongs to any one of these, okay, if pj belongs to any one of these, then definitely I know opt pj. If pj does not belong to any one of these regions, then pj is 0. And opt pj, in case opt pj is 0, opt 0 is 1, opt 0 is 0, basically. Because I do not take an interval in that case. I have set opt 0 is 0. Yeah, in case there is no interval, I set pj is 0, and I assume that opt 0 is 0, basically. Okay. So in that case, opt 0, I do not take its contribution to the weight is 0, basically. So that's all. So my statement is to compute j, in case this left part is filled up to j minus 1, then to compute j, I really need some constant amount of lookup. I need to look up pj minus 1, and I need to look up pj, opt pj, and I know what is the weight of j. I need constant lookups, and I can compute the max in constant time, and I fill this j. Okay. So computing every opt j is actually constant time. What is interesting is that how do I know this pj for every j? That is the most important thing. Remember, what is pj? I go back again. What is pj? I have sorted these intervals based on their finish time, and in this finish time order, okay, in this order, pj is the largest index. Let's say these are my indices now. Okay, this f1 prime, f2 prime, less than fn prime. So pj actually is the largest index in this order, such that does not conflict with j. So for every J, I need to know the Pj. Otherwise, how do I know what is my Pj? During this computation, basically, during this fill up of this table, I will be wondering what is my Pj. Okay. So basically, what you can do is you can actually scan. You can scan from left to right. Where is the thing? Pj definition? Yes, here. So what you can do is for a j down to n to 1, what you can do, I mean, you can compute the pj for every j. For the I equal, for j equal to n down to 1 in the sorted sorted interval, sorted set of intervals, find pj. So what you do, you actually linearly come back from n. So let's say 1 to, in this way, up to n. You linearly come back. The first, everybody is, and if you see that this is conflicting, then you just move left, conflicting, move left, conflicting, move left. As soon as you find that it's non-conflicting, you make that pj. Yeah. Similarly, then again, you start from this n minus 1, actually. You start from n minus 1. What is pn minus 1? Okay, what is, you start with this, and then what is the left? Conflicting, non-conflicting, conflicting, conflicting. And first non-conflicting, that is not conflicting with j n minus 1, you designate that as your pn minus 1. So for every j ranging from n down to 1, you need to actually compute pn. Okay. So potentially, I can say that for every n, I mean, in a very crude sense, I can say that potentially this j may conflict with anything with j minus 1. Okay, suppose this is the random index j, and I am interested to find pj. That means the largest I, that is smaller than j, that does not conflict with j. So potentially all of them up to j minus 1 may actually conflict with j. And in that case, I have to keep on searching in the left, so that I hope to find the valid pj, but it may not exist, or it may exist. But in the worst case scenario, I may have to search this entire space to the left of j. Okay, so that means for every j, I need to find out space left of j, all of it, all the left of j. So basically for n, I need to search worst case n minus 1 other space. For n minus 1, I need to search n minus 2 other such space. For n minus 2, I need to search n minus 3 other space. So basically, if I just sum up these values, I just sum up these values. These are the searching, basically, searching time. And up to basically say 2. Okay. So if I just sum up these, I just add all of them, then this will be actually order of n squared. So this much of time I need actually to compute the pj for all j. Okay. So once I have that computation, then rest is pretty easy. Okay. So I'm not discussing, but I am just leaving you one motivation or one interesting thing. I will ask you to find ideas that because these intervals are now sorted by their finish times, and I know, let's say I have an interval j and I have a random interval I, suppose. Okay, let's say I is less than j. Then I say that I and j are not conflicting if finish time of I is actually smaller than or equal to the start time of j. Okay, this is the only condition, because I know I is smaller than j. I comes before j. So I can only say if finish time of I is actually smaller than or equal to j. So using this condition and assuming that all the finish times are sorted, I mean, can we find out some better way, better than this order n square time, to check, to compute all EI PJ values for j, for all j ranging from 1 to n. Yes. Okay, how to do that? I ask you. I mean, this is, you can think of as a exercise. Okay, you find out. But if you go the naive way also, for everyone I just need to worst case search up to the max, all the elements of in the left. So that may lead to order n square. But I think this is the worst case scenario. Most of the on a random scenario, you can think of a better time. So anyway, so overall time is actually, if you pre-compute these things, then overall computation is essentially the filling of this table. Okay, and that can be done in linear time. Okay, so overall time actually is square, because you need to find these PJs. If you can improve finding PJ, then the overall time will be the time required to compute this PJ, basically, because this is essentially linear. Okay, and once you have this table filled up, you can actually find out the intervals that gives you the maximum width. Because once you fill this table, you just go back actually in the table and check what contributed your entry at a particular j. I mean, if at a particular point of time, let's say this part is contributing for the max value, then you know this interval, this in the list. Yes. Hello. Okay, I stop here. If anybody has any questions.
Sir, the assignment we have to submit to your email.
Yes. Oh, assignment. Okay, I will. Assignment is this program, right?
Yes.
This program that I told. I will actually notify you. Huh? You start doing it. Where is that assignment I wrote? Oh my God. This is the thing. Deadline is Saturday. That is tomorrow is 12/13, right? 13 to 21. Okay, so I will manage something. I will tell you how to upload it, because I will rather post it in the team. Basically, it will not fill my inbox. I will post it in the team as an assignment by today itself, and deadline will set to this thing. Okay. You just
Sir, the deadline is 13th, just to confirm.
yes. Today is 11.
Okay.
No?
And sir, do you want the indices of the elements in the set, or do you just want the maximum value?
Yes, I want both actually. I want write a C program, C++ or Java program to implement the max weighted independent set problem. So problem means actually both. I need actually the max weight as well as the set, basically. And remember, here the input, how do you take the input? So input input is given in a file, suppose. Okay, I mean input has to be, I mean, you will not give the input. Some graph is the input, right? So input, let me tell you how, just 1 minute, how you will take the input. Input will be file actually. It's a file, file. So in the file, it should be basically the edges of the graph. Let's say A, B, C, D, and the weight. Blah, blah, blah. Say MN. So every edge will be there and the corresponding weights will be given. So if every edge and the corresponding weights are given, then this clearly represents all the graph, all of the graph. This should be taken as the input. So how you, this will be given in a plain text file. Okay, plain text file. One vertex will be no vertex, nothing. Basically edges will be given. Once you have edges, then that represents the graph because it's clear, right?
And the
Remember,
number of edges in the first line, if possible.
no, you do not need that because see, if you make a first pass through the file, then you know how many row entries are there, and that gives you number of distinct edges.
Okay, sir. We can do that.
The number of edges.
Sir, we are considering a chain only, or it can be of any form, the graph?
It's a chain problem that I have given, right?
Yes, sir. So we are solving for the chain one itself, right?
Yeah. Chain only. This way of doing it does not work anything other than chain. I mean, we will see later where it works, but in general graph, it may not work actually. So in that case, you may say, okay, I can reorganize the input in a better way, but I don't want that. I want everybody's input should be in this text file. I just need to give the input like this, edge and the corresponding weight, edge and the corresponding weight. That should be my input. But there should be no repetition in edge. I mean, repetition should be, I mean, if you are intelligent, your program should detect the repetition and delete it, essentially.
Sir, do we have to make an input file also?
See, if you do not have input file, then how I will give a random input, right? I have a standard input, but I want you to try with your input, and then I will check whether it works with my input.
Okay, sir. And the format of your input, like, will it be A, comma, B, comma, W1, or will it be space separated there in each line?
What do you mean by A, comma, B, comma? I don't understand.
Like in the text file, in the first line, will it be, how will the characters be written? Will it be A, comma, B, comma, W1, or A space separated, A space, B space, W1, something like that?
It's a basically three value. It's a three values separated by space. Say U, V, W. U is the vertex, V is the vertex, and there is an edge between them, and W is the corresponding weight.
Yeah, okay, sir. Thank you very much, sir. And sir, the vertices would be between 1 to n, or like would they be characters?
I don't care. Do I care actually? See, once you have these edges, then if I try to draw a graph, I can immediately, if I draw and visualize, it will immediately lead whether it's a valid chain or not. It does not mean I have to give the chain in a sequential way.
Okay, sir.
Right. I can give the first stage, then last stage, and etc. etc. Isn't it?
Yes, sir, I got that, but I was just asking about data type of the like vertices, the labels U and V. Would they be characters or would they be integers, like ranging from 1 to n?
It make any difference?
It will.
It may make a difference to you, but it doesn't make any difference to me. I will like to give any input.
Oh, okay. I got it, sir. Now, I
Okay.
understood. Yes. Thank you very much, sir.
Yeah. Okay. So we stop here today.